There we go.
Hello.
Thank you. So I guess this, Jen was saying this is the second in-person seminar we've had this semester. Oh, third. Oh, maybe he meant second visitor. Maybe you had. That's good. Yeah, we're also in a weird hybrid situation at Rice. Some people calling in, some people visiting. So people have been returning to campus, I guess. Everybody teaching it on campus this semester?
Yeah, all the classes are.
Yeah. Yeah, they tried even last fall to have in-person teaching. I was on campus for the first 2 weeks, but the students, it was optional, so none of the students came. I'm not going to drive 20 minutes to get here to teach an hour-long class to 2 people, and the other 10 people are on Zoom. So I did it from home.
That was last year.
Yeah, that was last year. So now, as of last April or March or May, maybe April and May, everybody started filtering back onto campus, and all the classes are all in person now. Yeah, it's with a mask. If it's fewer than 10 people, you don't have to wear a mask. And if it's more than 10 people, you have to wear a mask, except for the instructor, if the instructor is more than 10 feet from the closest person. But the rules have been evolving because we do testing every week. And so they know if you're vaccinated, you should get tested every 2 weeks. And if you're unvaccinated, every week. It used to be every week for everybody, but as the rates were going down, but the university provides testing. I mean, for us, it's not. Yeah, we're not mandating a vaccine. It's not exactly mandatory testing either, in the sense that they want you to go. They tell you to go, but nobody's checking up. But it's also free. I mean, every time I take a trip, I'm sure to go. I want to take a trip.
You check online how many are there?
Yeah, it looks like we got 5, 6.
Hey, Andrew, can you hear me? Oh,
It wasn't able to make it. So he's out of town.
oh, no.
It says
Oh,
he's online, but he's saying I can't hear them.
Oh, are they saying something?
I mean,
oh,
Raymond
no.
says I am speaking. He's texting I am speaking,
okay.
but we can't hear him.
Oh,
Do we want
The
to?
audio is not connected.
oh, but maybe he's muted by the host.
Oh, I'm not muted.
Oh, he's not muted.
No, he's not. I guess your computer is not connected audibly. No, but that's impossible. Okay. Well, but Raymond, you can hear us, right? Can maybe if you have questions,
Oh.
you have to ask and type. Hello.
Oh,
I'm not on the Zoom call, so
You're
I'm
not.
not in. I guess I'm.
Okay. This computer is connected to Zoom call.
I mean, if you could, I guess if you could go on Zoom,
Yeah.
see the question. I can try to keep an eye on the chat too.
Yeah. Okay. I can look at the Zoom. No problem. Yeah, it'd be nice if people ask questions. Yeah. Do you know how to turn up volume for the?
I mean, this is
mic?
yeah, I did that. I mean, it's
Okay.
this is at max, but I don't know.
Okay.
I don't know why it doesn't.
Speaker.
Oh,
Let's see.
what if you just do MacBook Air speakers? Right?
Yeah.
Then it should come through here.
Maybe let me do system. Raymond, can you say something?
oh, hello. Do you hear me? Hello, hello, hello.
I think this
Hi.
is connected to the system, right? I don't think that's even connected to just a.
Okay, good.
I don't know.
Oh,
Okay, at least we can hear on this computer.
Yeah,
So
that's
if
fine.
you can hear the question and maybe you can repeat the question.
Yeah.
For the audience couldn't hear. Okay, great. So today we are super happy to have Andrew Lang from Rice University to give us a talk on X-ray signature of Axion emissions from compact stars. Just a really quick and brief introduction to Andrew. Andrew graduated from University of Wisconsin-Madison and did the postdocs at Arizona University, Arizona State, I forgot which one.
Arizona State.
University, and U Chicago at the KICP. And he worked on the vast different type of topics in particle physics and astrophysics and cosmology. And he worked on many important works on those different fronts. And today he will give us this particular talk, and we're really looking forward to it.
Yeah, thanks, Jen. I mean, thanks also for the opportunity to come visit and catch up with people and get out of my house. It's nice to be giving in-person seminars again. So yeah, the plan for today is to talk about X-ray signatures of Axion emission from compact stars, mostly white dwarf stars. We've also been thinking about neutron stars, but I won't have time to talk about it. If you'd like to discuss that at the end, feel free to ask. The question I want us to be thinking about then for the next hour is, do magnetic white dwarfs emit hard X-rays, by which I mean X-rays with energies above a few keV? And the answer to the question is simply that we don't know. We haven't spent any significant amount of time looking at white dwarf stars with telescopes that can measure X-rays at these energies. And as a result, we just don't know whether these stars are emitting hard X-rays. The reason we're not looking at these stars is because they're not supposed to be emitting hard X-rays. An isolated white dwarf doesn't have any mechanism of generating a X-ray at energies above a few keV. It would be different if the white dwarf were in a binary system or if it were accreting with a disk.
What's the surface temperature?
I'm sorry?
What's the surface temperature?
Surface temperature is about 10 to the 4 Kelvin. So 10 to the 7 Kelvin is a keV. Yeah, so the thermal glow from the surface is not.
So twice as hot as the sun, our sun.
Yeah, they're around as hot as our sun. There's some order 1 variation in temperatures across stars, which I'll have a table at some point, but that's about right. Where the temperatures are comparable with the sun. Now, although we don't have a reason to expect that these stars are emitting hard X-rays through ordinary astrophysical processes, there is a good reason to expect that these stars might be emitting hard X-rays, which is to do with the physics of axions. If axions are getting emitted from the core of the star, they can then be converted into X-ray photons as they pass the star's magnetosphere. And in this way, the energy of the X-ray would be tied to the energy of the axion, which would be tied to the temperature at the core of the star, which is closer to 10 to the 7 Kelvin or around a keV. And so, if I'm going to essentially argue that one should expect hard X-ray emission from compact stars like white dwarfs and neutron stars from this physics. And the exciting thing is that if you were to observe these stars then with an X-ray observatory like Chandra, we may uncover evidence of this thermal X-ray emission associated with the core temperature of the star. And we were studying this a few years ago with Ben Softy and his student Chris Desert, and around the same time we were putting out our paper, Chandra was having a call for proposals where they were asking people, what should we spend time staring at with our X-ray observatory? And we were fortunate enough to have things line up. We were able to put in a proposal and they accepted it to spend about 11 hours staring at my new favorite star, REJ 031783, which you'll hear a lot in the next hour. You'll hear me say a lot in the next hour. So they did this observation actually last winter, and I'll report on the results of what they found.
But these magnetic fields are going to be very large around the star, right?
That's right, yeah. So the magnetic field around a white dwarf can be megagauss to thousands of megagauss. It's not as high as a more compact neutron star, but it's quite large.
Which is what people call magnetars.
That's right, yeah. If you have a neutron star with a magnetic field cranking all the way up to 10 to the 15 Gauss or so, we would call it a magnetar. And I'll talk about how you get sensitivity to the same sort of physics from neutron stars as well. So the plan is I'll very briefly say a few words about axions to get us all on the same page and how we're searching for axions for a variety of different observables. Then I want to talk about this signal that I've just alluded to, X-ray emission, axion-induced X-ray emission from compact stars. And I'll talk about what we can learn from existing observations of magnetic white dwarf stars, and I'll end up talking about the results from this Chandra observation. So very briefly, we're going to be thinking about Axion-like particles, pseudoscalars with a mass that's somewhere down around milli-eV or anything lower than that. We're going to rely on the fact that this axion couples to ordinary matter through photons and electrons, which are the couplings required to both produce axions at the core of the star and then convert them into X-rays in the star's magnetosphere. And of course, these interactions are dimension 5 operators, and so the couplings are tied to an energy scale of new physics, which in the case of a QCD axion would be Hitch-Quinn scale, or an axion-like particle would be some other UV scale. So suffice it to say, if we were able to detect axions through any means, not necessarily, of course, just from compact stars, this would be direct evidence for new physics. We would be indirectly learning something about a new energy scale in the UV that we can't access directly in the laboratory. And there'd be connections with the strong CP problem for the QCD axion or theories of the compactified extra dimensions like string theory and Axiverse. There has been obviously a lot of work in searching for axions, the QCD axion, as well as axion-like particles over many decades. And I'm not going to summarize each of the different constraints. I just want to highlight that it's remarkable that when we go looking for axions, we use essentially every tool that's available. There's terrestrial probes, such as the ADMX experiment, or some of these more broadband things like ABRA. There's astrophysical probes, such as CAST. And then there's cosmological probes, such as Big Bang nucleosynthesis. And so by employing all of these tools collectively, we're hoping to, at some point, pin down the axion. There's a couple of things that I've been thinking about in recent years that I won't have time to talk about. So for this slide and the next one, I just wanted to remark upon that. Working with Mustafa Amin at Rice University and our postdoc Mudit Jain, we've been thinking about cosmological observables that could be tracers of axion-like particles, specifically CMB birefringence, and how observations of the CMB polarization would be affected by the imprint of cosmic axion strings in the universe today. So with future observations of the CMB, we might unveil the presence of these axion strings and learn something about physics at high energy scales.
We don't expect many strings to be there as of today, right?
I mean, compared to a local string, which is decaying predominantly by gravitational wave emission, it's very slow and inefficient. You have lots and lots of local strings, and compared to you have many fewer global strings. But you're still looking at all of the strings that were present between redshift 0 and surface of last scattering. So you can get, I don't have a map of the sky, but we've been generating mock sky maps. You can clearly see lots of stringy features. And working again with Mustafa Amin, Paul Safin, and our postdoc Donggang Mo, we've been thinking about solitonic configurations built from axion-like particles, compact axion stars, and the resultant electromagnetic radiation that occurs when these are exposed to electromagnetic fields. Maybe one could imagine one of these axion stars passing through a neutron star magnetosphere, and the incredibly strong magnetic field there would lead to transient signal that could be detected.
Just quickly, that is an axion style pole.
I mean, one could imagine that even at as an initial condition, the axion field is misaligned to some semi-homogeneous value displaced from the minimum of the potential, and then provided that the axion has some attractive self-interaction, either gravitational or non-gravitational, localized, that the homogeneous field will begin to oscillate and fragment into clumps, which are axion stars. These stars would be ones formed through the non-gravitational self-interaction with the axion-like particle. Yeah, so I mean, the self-interaction doesn't have to necessarily be too big. I mean, but to get this electromagnetic signal, the coupling to electromagnetism must be fairly large.
How big are these stars?
These ones are to be very compact, like a centimeter. It depends on FA and axion mass, but a centimeter is the kind of number to have in mind. These are the compact class of axion stars rather than the dilute ones, which are bound by their gravitational self-interaction and then would be much, much larger than an ordinary star.
And what mass?
I think, what was the mass? I've forgotten the number off the top of my head. But I mean, it's not a macroscopic mass.
It's more like a rock.
Like a rock, yeah, that's true. I mean, I'm not coming up with the names. I also agree that it's kind of funny to call it. There's obviously no fusion. It's not glowing. It's just a cloud of axions that are.
It's just an overdensity.
That's right.
A bound overdensity.
That's right. Yeah, it's a soliton that's built from axions.
External experience of this EM radiation, because in principle you have the axion that is sort of oscillating.
That's right.
So I thought in principle you don't need any external source, like you can just induce the EM radiation from this oscillation of the axion.
Yeah, there can be a parametric resonance. I mean, it's essentially an A E dot B type interaction. So as A oscillates, you can have a parametric resonance that amplifies the electromagnetic field. But and that's essentially what you're seeing happening here with this this growth. But if you have a background magnetic field, then now there's a mixing between the axion and the electromagnetic field. Essentially, the axion star acts like a charge dipole, and then you get ordinary dipole radiation. So this figure is showing that for small axion photon coupling, the main emission channel is that dipolar radiation. But as you start cranking the axion photon coupling, the parametric resonance effect that you're interested in would start to be dominant.
And the self interactions that are non-gravitational, are those added, or is that just in theory anyway?
I mean, one could imagine just using the cosine potential of an axion-like particle. That particular potential isn't especially efficient. One can imagine these types of potentials where it flares out like it plateaus. That turns out to be more efficient for forming the axion stars, keeping them bounded, especially keeping them around longer, because the compact axion stars are unstable. Sooner or later, they're just going to start spitting out individual axion-like particles and dissipate. So if you're interested, yeah.
Just to be clear, because now you're sometimes you're using axion, sometimes axion-like particles. So are we talking about the QCD axion, or are we not talking about?
Yeah, we are never talking about the QCD axion, and please forgive me if I don't want to say the whole axion-like particle.
So
No, okay, just if you say it once, then we're set.
Yeah, thanks. Yeah.
You'll be at the left of this plot and above, right?
You're asking where is the QCD? Oops, I'm sorry.
In this landscape of models, there is this QCD line, so
Right.
it will be above this line and to the left.
That's right. Yeah, that's definitely correct. We're thinking about, yeah, so maybe I didn't introduce this plot, but here we're thinking of the familiar axion-like particle parameter space. Horizontal axis is axion mass, vertical axis is axion photon coupling. The diagonal band is where the QCD axion models live, typically KSBZ and DFSC. And we're going to be thinking about parts of the parameter space that are up here somewhere. For both the things I've just mentioned here as these bonus topics, as well as what I'm primarily going to be talking about, the compact stars. Yeah, so suffice it to say, there's a growing interest in studying axion-like particles, and I think it's nice to see an exponentially growing curve that doesn't fill us with dread. I guess this one is pretty out of date now. It was sometime last year. Fortunately, it's dropped off a lot. Hopefully, the one on the left won't drop off a lot anytime soon.
So we're predicting the axion hardness will decline.
Yes. Hopefully not.
Yeah,
It's
vaccinated against that.
Yeah, I guess it's unsustainable to have continued growth. Firefox wants to do an update. Maybe we'll save that for later. All right, so let me talk about the signal that I alluded to at the beginning, where we're looking for hard X-rays from compact stars. Very quick, get everybody on the same page. What is a white dwarf star? These are old stars that have exhausted their nuclear fuel and no longer are burning through fusion. They consist then of a degenerate ball of electrons. Of course, if it were just electrons, they would have a whopping huge negative charge. So there's a compensating number of ions to ensure charge neutrality. And the ions provide most of the mass of the star, because for each electron, there better be a corresponding ion. The mass of the star is then around the ordinary solar mass, but the radius is a lot smaller than ordinary solar mass, only about the radius of the Earth, 1/100th of a solar radius. Temperatures are comparable to the temperature of the sun, but the luminosity is a lot smaller because the area of the surface area of the star is smaller. Core temperatures are in the ballpark of 10 to the 7 Kelvin, which is again around a keV. And importantly, the magnetic field strength of these stars is quite large, 10 to the 6 to 10 to the 8 Gauss. And this you can understand from the fact that our sun, stars like our sun, have order 1 Gauss magnetic fields. If I compress that magnetic field down to 1/100th of its radius and 1/1,000,000th of its volume, the field strength will grow by a commensurate factor up to about 1,000,000. And I'll talk about some stars for which we've actually made measurements of the magnetic field strength and how we make those measurements, give you some values to have in mind. Regarding populations, the closest star to Earth, Sirius B, is a white dwarf at about 8 light years away. And it's expected that most of the stars in the Milky Way galaxy, given stellar evolution modeling, should be white dwarfs. And this is favorable in the sense that I want to talk about how we could use white dwarfs to go looking for axions. There's lots of candidate stars out there. Now, the emission of axions from white dwarfs and compact stars is not a new topic, and it's been explored extensively starting as early as the 80s. For white dwarf, axion emission predominantly results from the scattering of an electron on an ion, and axion is then produced this Bremsstrahlung process. The luminosity of axions through this type of scattering is then at around 1/10,000th of a solar luminosity. If the axion electron coupling were around 10 to the minus 13 and the mass of the star were around a solar mass and the temperature at the core of the star were around 10 to the 7 Kelvin, which are typical numbers. So if you're thinking of axion-like particles existing in nature, you should, and if you're thinking of them coupling to electrons in stars, then you should be thinking of stars like our sun and white dwarfs here as glowing not just in photons, not just in neutrinos, but also glowing in axions. Now, if these stars throughout the universe are glowing in axions, maybe that nearby Sirius B star is glowing in axions, can we detect those axions when they reach a laboratory here on Earth? So we'll do a quick back of the envelope estimate to get a sense of whether we're going to be able to detect these axions upon reaching Earth. The axion luminosity I gave on the previous slide, it was 10 to the minus 4 solar luminosities for some fiducial axion electron couplings. We calculate the axion flux at Earth, energy per area per time, by dividing out through the distance to the star, which is maybe tens of parsecs. Once the axion reaches Earth, how are we going to detect it? One way of detecting axions is to expose them to a magnetic field, and then they have some probability of being converted into photons, carrying the same amount of energy. And the axion photon conversion probability is roughly given by the square of the axion photon coupling, the square of the magnetic field strength you're applying, and the distance L over which you've applied that magnetic field. Putting the factors together gives an estimate for the axion-induced photon flux in a detector here on Earth, which is at the level of 10 to the minus 31 ergs per centimeter squared per second. That number might not mean much to you, and it didn't actually to me when I first estimated this, but if we were to calculate the number of counts per second, that would correspond to something like 10 to the minus 18 counts per second, because we know how much energy the axion is carrying. And so that's an incredibly low rate. It's less than 1 event per age of the universe. And so this strategy of waiting for the axions to reach our laboratory is not a good way of testing the idea that axions are being emitted from white dwarf stars.
So these are normalized to specific axion couplings. Why are those chosen? 10 to the minus 13.
Right. So I've done the most optimistic thing I could do in choosing all of these fiducial parameters. The axion electron coupling is constrained to be less than 10 to the minus 13 from observations of white dwarf stars and the fact that they aren't cooling down faster than they usually do through neutrino photon emission. And the axion photon coupling is constrained by CAST's observation of axions, search for axions from the sun. So these are the largest possible values for those two couplings given those existing limits. And moreover, I did pretty optimistic things, I think, in regard to the other parameters. This star is fairly close to Earth at only 10 parsecs away. And I assumed that in our laboratory, we had produced a magnetic field of 5 Tesla and over a volume of order 100 centimeters, which is a relatively strong field over a relatively large volume.
The reason is also 10 minus 11, 10 minus 13 is aberration is because in one case you normalize on GDP, in another case on MU because of There's two. of them.
Yeah. That's true.
So they're roughly same. Right? So numbers.
Yeah, the units are, that's right, the units are. Now, of course, if we were able to produce a magnetic field in the lab that were many orders of magnitude larger, maybe this would be, this type of strategy for searching for Axion emission become viable, but we don't need to produce, I mean, we can't produce a much stronger magnetic field in the lab. But moreover, we don't need to in the sense that the compact star from which the Axion was emitted already provides a very strong magnetic field. Neutron stars, magnetars, as Tony was asking about, have field strengths at the level of a trillion to a whatever 10 to the 15 is, 10 to the 15 Gauss, 10 to 50, anyway. And magnetic white dwarfs have 10 to the 6 to 10 to the 9 Gauss strength magnetic fields. Again, it's because neutron stars are smaller, so the field strength they have carries larger. And so one could make use of these incredibly strong magnetic fields at the source to accomplish the Axion photon conversion. And several people in recent years have been exploiting this idea, in particular in the context of neutron source magnetars. Sorry, I just realized this label should have been changed. So for instance, the context of magnetars, this collaboration was looking at the same sort of process I'll be talking about for white dwarfs. And Jerome, Raymond, and Co. and collaborators were looking at emission of axions from a particular set of neutron stars known as the Magnificent Seven, where they tried to identify an anomalous X-ray flux. So the label above there is wrong.
Sorry. I seem
Yep.
to remember that when people were looking at the signals from magnetars, that the environment was just too dirty, that you wouldn't be able to tell it's coming from an axion.
Yeah, there is an issue of, could the axion rescatter before, does it actually get to us? I mean, you need not the axion, the photon, right? Because once I've converted the axion into the photon, the cosmic medium, it's not even a cosmic medium, we're still an interstellar medium, between us and the star will be transparent to X-rays, but does the environment of the star allow you to escape? That's one of the several reasons why it's a bit messier to do this with neutron stars than with white dwarfs.
So you're saying that white dwarfs would be a cleaner environment?
Yeah, in the collider analog, it's like when we talk about hadron machine versus Z plus E minus machine. One is for discovery, because the neutron stars in particular, there's already a lot of data on neutron stars. That's why your colleague Raymond and collaborators were able to use available X-ray observations of neutron stars to search for evidence of axion emission. But it's a dirtier calculation in the sense that there's other ways that neutron stars could be producing X-rays. They're supposed to produce some level of X-rays, whereas the white dwarf stars aren't supposed to produce any level of X-rays if they're isolated and not accreting. So that's one of the advantages of using white dwarfs. So, just to reiterate, that's what we're going to be doing for the rest of the talk. We're thinking about emitting axions through this electron-ion bremsstrahlung scattering, and then using the axion electron coupling here, and then converting them into photons using the axion photon coupling in the star's magnetosphere. And the signal is roughly just this product. We would like to know what's the flux of axion-induced X-rays reaching Earth and what's their energy spectrum. And this is going to be the product of the axion luminosity spectrum at the star, the axion photon conversion probability, and some geometrical factor associated with the distance to the star. So I'll just quickly talk about how each of these factors are calculated in 1 or 2 slides apiece. Putting them together will give us the shape of the signal.
Okay, I may ask a super dumb question. So why do you make Axion electron couple? Why don't you use Axion neutron?
Sorry, you could, this is an ion, by the way. I should have labeled that as maybe A comma Z would be a better, I guess N was meant to stand for nucleus. Yeah, of course, that's a great question. I mean, you can rely also on the axion nucleon coupling, or also the axion photon coupling. I will mention a little bit about what happens from the axion photon coupling, although actually it might be in the back of the slide, so we could always do it at the end. The limits you get from this axion photon coupling just aren't as strong as existing limits from CAST, for example, because there's an extra factor of temperature over electron mass for that emission rate. And similarly, the limits you get from axion and nucleon coupling just aren't as strong. So the best channel would be allowing for axion emission of the electron.
Just basically come from the fact that this product is the least constrained one compared to the other ones.
It's not, I mean, this particular, yeah, so obviously that's a great point too. The signal I'm going to be talking about is dependent on the product of these two couplings. There aren't that many other observables that depend specifically on that product of couplings. CAST does a similar measurement of our own sun where they get a limit on that product of couplings. But what I'm talking about is individual limits on separately on the axion electron coupling, axion photon coupling, and axion nucleon coupling from different observations, right? Yeah, for instance, the axion photon coupling is so strongly constrained by CAST already that I can emit axions off of the photon here, but it wouldn't lead to observable signals if I'm in the regime that's consistent with CAST.
Is there one emission in solar emission? People like they don't calculate a detailed spectrum with lots of lines, right?
From our sun?
Yes. So you're talking about free emission or
Yeah, free. Yeah, so that's a free electron, free ion. You're talking about Axion over combination, where we're going to capture an electron on an ion.
that would be bound, free to bound, right?
Right.
There could be just transitions. They're not fully ionized, are they?
Not fully ionized, but I mean, the electrons are degenerate in the neutron star, which is a bit of a different, there's a different medium than in our star.
So there are no lines.
Yeah, no lines, yeah. Yeah, it's, the processes that dominate are star dependent. So the processes that are most relevant for our sun are like these ABC processes, which involve Axion over combination. Whereas here, this channel, electron ion Bremsstrahlung dominates. We're going to talk in the next couple slides then about these two factors. So very briefly, I mentioned that there was work in the 80s on studying axion emission from the core of compact stars. And so this is, I'm just quoting that result here. The axion luminosity spectrum then is the product of these factors, the axion electron coupling, as you'd expect, a bunch of constants associated with the electromagnetic interaction of the electron in the nucleus. The energy spectrum is thermal. There's a factor of the mass of the star because we have to integrate over the entire volume of the star, and the emissivity is proportional to the number density of ions. So they provide the dominant mass. So when I integrate that number density over the volume of the star, I just get a factor of the mass of the whole star. And then there's a factor that depends on the properties of the ion on which we're scattering, its atomic number and mass number, and some other factor F, which is order 1, but depends on the particular phase and species of the ion. We'll come back to that towards the end of the talk. But for this part of the talk, you can just imagine that F is set to order 1, and then Z and A are chosen because maybe we're thinking of an oxygen neon white dwarf. The ions are predominantly just oxygen neon. The point being that if I could see the axions directly, I would be seeing a thermal energy spectrum, where this temperature in here is the temperature of the core of the star, not the surface temperature, around a keV. And this calculation is being done assuming the axion mass can be neglected, which just means that its mass is below a keV, and we'll be interested in down by MeV or below anyway. So that's perfectly fine. The other thing we need to calculate then is the axion photon conversion probability. And so this axion photon conversion occurs because this dimension 5 operator can be written in the form axion field, electromagnetic field, A, vector potential A, and I mean, this is A E dot B. And in the background magnetic field, this leads to a mixing between the axion and the photon fields. And so that's described by this 3x3 mixing matrix, which gives the evolution of the axion and photon fields with distance propagated through the background magnetic field. And these terms highlighted in red are the result of the axion photon coupling. So you can see how those terms highlighted in red are proportional to GA gamma gamma, and they're also proportional to the background magnetic field. So if I either turned off the background magnetic field or I turned off the axion photon coupling, the red terms would go to 0, the axion would decouple from the photon, and there'd be no more axion photon conversion.
Do white dwarfs have coronas? Because, I mean, like, this stuff is typically, depending on the mass, very sensitive to the presence of absence of ionized.
The photon mass, I mean, yeah. So there is, with the neutron stars, that plays a more important role, but the white dwarf stars plays a less important role. And specifically, if the reason it plays an important role with neutron stars is because as the density of electrons grows as you move closer to the star, going from outside the star towards the surface of the star, plasma frequency grows. And there can be a point at which, say, the axion mass crosses the plasma frequency. At that point, you get a resonant enhancement because of some of these on-diagonal terms drop to zero, and the mixing angle is very big. So people have exploited that fact to search for axion dark matter that was not produced at the star, but just falling onto the star, which would then produce a radial line when at the point where the axion mass crosses the axion. Yeah. In this context, we're using a non-resonant axion photon conversion. So the plasma frequency around these stars is a lot lower, and we're not in the regime where the axion mass is going to cross. This is a non-resonant conversion. For this formula, I grabbed from a set of notes where I had written the axion mass, but we're not using the axion mass. I should really scratch that out from the slide. But the other thing I did want to emphasize is that in addition to these operators, this operator that's responsible for the axion photon conversion, there's also a photon self-interaction, the Euler-Heisenberg terms that result from integrating out an electron loop. And so you can see here they've got electron mass in the denominator. These typically wouldn't play an important role, but we're going to be in a regime where the magnetic field strength is so large that these 4 photon terms, which are like E squared, B squared, or EB, the B field is so large that they modify the dispersion relation for the photons and contribute additional terms on the diagonal. So, for instance, these blue highlighted terms are the result of the Euler-Heisenberg 4-photon self-interaction, and they also show up on the diagonal. So if I really crank up the magnetic field a whole lot, I'm going to start putting additional terms on diagonal, and thereby reducing the mixing angle also. And turns out we're going to be in the regime where the magnetic field is actually that large. I'll show in just a second. So this is the essence. Yeah, go ahead.
With the classification of the previous page, right? You said you are essentially describing the signal emissions. So, but doesn't this go against your argument earlier? Like you are going to observe KEV conditions, so that is much higher than the temperature of the white dwarf.
Yeah, what's important to recognize is that the core temperature, the material inside of the white dwarf has a very high thermal conductivity. So the temperature in the interior of the star is almost uniform out to basically the surface of the star. So the temperature profile drops off really steeply from 10 to the 7 Kelvin, which is around a keV.
So basically,
10 to the 4.
Axion to carry the energy from the core.
That's right. Yeah, the axions are helping energy escape from the core of the star. In sort of the same way that, the way stars typically cool is through neutrino emission, the same sort of physics of the neutrinos seeping out from the core of the star. So this T is the core temperature. I should put a C there, I think. Good. Thanks for asking. The way we do this in practice is we sample points inside the star, draw a straight line out of the star, look at the magnetic field along the straight line, if you assume some dipolar profile for the magnetic field, and solve these equations, do this integral. And then the initial condition is taken where the axion wave function is 1 and the photon wave functions are 0. And then the axion photon conversion probability is the square of the photon wave function divided by the axion wave function at infinity, where the magnetic field has dropped off. We can do that numerically then in practice, but to give you a handy formula, let's make some simplifying assumptions so we can actually do the integrals analytically. First, we'll assume that the magnetic field is all oriented in the same direction, which is maybe has some transverse component to the direction of propagation of the axion. And we'll assume that the field strength is dropping off like it would for a dipole, meaning it goes like 1/r². So in that case, you can solve these equations. Firstly, the 3x3 equation breaks down to a 2x2 equation. You make an assumption about the orientation of the magnetic field. And then you can actually do the integrals analytically.
How well is it known, like for the sun, it's a turbulent field, right?
Mhm.
It's not a regular field.
Mhm.
And so here is what's the assumption?
Yeah, well, I mean,
Because you can imagine that if there's domains of completely different
Yeah.
orientation, there will be a self-compensation.
Mhm. Yeah, I mean, we're fortunate that the white dwarfs are much quieter, older, no longer burning systems. So you'd expect the magnetic field to have a smoother profile.
So
And-
regular.
Yeah, and moreover, so I'll talk shortly about how we can measure the magnetic field of stars like white dwarf stars. And there's this one star, REJ 0.3 that I mentioned at the beginning, for which we actually have a lot of information about the structure of its magnetic field, which is consistent with it just being a simple dipole. I'll talk about that just in a few minutes. When I said I do the numerical calculations, I'm assuming it's a dipole.
Is it known why there's such a large regular?
I don't have any more insight into that. Maybe others know. I don't know. I mean, I think it's reasonable to expect that if the star is not,
Should be much less turbulent.
yeah, because it's not as active.
I was just
Yeah.
just wondering why such a huge difference in the size of the magnet compared to the sun.
Strength, though.
It's more compact.
Yeah, that's the,
More compact
that's
with the regular one, yes, something supposed.
I mean, it had to have been there before, right? It doesn't get, you don't get any extra, right? So whatever was there before, and it's just that now it's stronger because it's more compact, right? What else can?
yeah, you've squeezed a 1 Gauss field in 1 solar radius down to a 1,000,000 Gauss field in 1/100th of a solar radius, and the volume decreases by a factor of 1,000,000. But as for this,
You can't get it anywhere else. Right?
Yeah.
So the total energy in this field might be, you're saying, similar to what.
Oh, if you integrate it,
Right.
sure.
Yeah, okay. Okay.
I'm guessing.
Yeah.
I mean, that would be the reasonable.
But the particles, the ions that are producing this field are now different, right?
the chemical composition of the star has changed. I mean, we now have, it's going to be,
But there's still some moving charge in the middle, right? In the center of the core.
I mean, I don't know if you're talking about a bulk flow of fluid or we're talking about just thermal scattering. I mean, it's- I mean, there's an electron degeneracy pressure that holds the star up against gravitational collapse.
That is not necessarily magnetized.
But what's the source of the magnetic field, you mean?
Yeah, yes, of course.
Is it the moving ion, the oxygen? And
Yeah, I know, yeah, probably, yes. I guess we need to satisfy Maxwell's equations. I want to have a magnetic field. I probably need a current.
So this is known from the spectrum, right? So.
Yeah, I will talk about how we learn about magnetic fields of specific white dwarf stars from looking at their spectra shortly. That's a good question. All right, so just to reiterate, if we make some simplifying assumptions over here, then we can get an analytic expression that solves this equation. So let me just write that down for you. So again, I assumed that the magnetic field strength was dropping like 1/r cubed, which is what you'd expect for a normal dipole. We integrate the previous equation, calculate the ratio of the photon field squared over the axion field squared far away from the star. It's given by this expression, which involves some gamma function and a generalized gamma function, so some special functions in there. And it has familiar features. So remember, delta B was the guy proportional to the axion photon coupling. So if I send that to 0, my axion photon conversion probability better drop to 0. So that bit checks out. And we can make a plot then of how the axion photon conversion probability varies with the strength of the magnetic field at the surface of the star. It drops off like 1/r cubed further away, holding fixed the axion photon coupling to some arbitrary fiducial value. It's probably 10 to the minus 11 for this plot, 10 to the minus 11 inverse GeV for this plot. If the field strength at the surface of the star were relatively small, then as I push it upward, the axion photon conversion probability also grows, and it grows like the square of the magnetic field. And that's the same scaling relation I gave a few slides ago when we were imagining trying to detect the axions upon reaching Earth, the B squared, G gamma gamma squared, L squared scaling. However, if I crank the magnetic field strength up sufficiently past tens of megagauss or so, that scaling B squared softens to only a B to the 2/5. And this is the consequence of that Euler-Heisenberg 4-photon self-interaction. Because remember that term, it's like EB. In the presence of a strong background magnetic field, it's adding a new term to my mixing matrix on the diagonal, and thereby reducing the mixing angle and the conversion probability. So for very strong magnetic fields, we still gain in the sense that we get more efficient axion photon conversion as I turn up the field strength, but we no longer gain like B squared. We only gain like B to the 2/5 power. So one consequence of this is just that if I'm surveying a whole mess of stars and I want to know who's going to be best for getting Axion-induced X-ray emission, the stars with the stronger B fields are better, but not necessarily a whole lot better. By the time you're up at, say, neutron stars, I mean, you can do better with neutron stars, for instance, if you're at 10 to the 12 gals, but you don't gain as much as you might have naively expected from the B squared scaling. The question. Yeah.
If you're so sensitive to Euler-Heisenberg, does that mean you could go to a higher order and get even more?
I don't think you're not in violation of the EFT.
I mean, I could put more EVs in the numerator.
Yeah, I understand. Yeah, I think the EFT is still valid. So the higher order term.
Well, they are more suppressed by magnetic field to the
Yeah. Yeah, it's just what's happening is that when I compare with the other on diagonal terms here, right, we're looking at, this is one of the entries on the diagonal. And then this combination is really small. I solved this for 0 because I have an on-shell axion to start. So this is 0. And then this is basically axion mass squared over 2 axion energy, which is very small. And so I don't have to turn up the field strength all that big until it starts to become important. But you're right, I could have another term, but I think it's even smaller by another B squared over M.
Sometimes people just critical field, right? And things like that.
They do what, sorry?
Critical boundary.
Right, yeah.
So if he was below that, then it means that he was
Yes.
by the lowest.
Yeah, we can define ME squared over alpha as a critical field. And then the EFT works as long as B is less than B critical. And that's very high, way above what we're talking. I forget the exact number, but maybe 10 to the 16 something. Okay, so we calculate. We asked some people. We read some papers from the 1980s that told us how to calculate axion emission from the core of the star. We solved a 2x2 matrix or 3x3 matrix to get the axion photon conversion. We put the factors together, and now the expected axion-induced X-ray flux at Earth due to axions emitted at the core of the star and converting to photons in the magnetosphere looks like this. Here's an energy. Here we're making a spectrum. Energy is measured in keV. The blue curve is the intrinsic axion luminosity. If I could see axions and if I were sitting, yeah, I could see the axions. And so this is just that thermal spectrum I mentioned a little while ago. And then for the fiducial parameters I chose over there, the axion photon conversion probability is relatively energy independent and on the order of 10 to the minus 4. So the X-ray spectrum is down by a factor of about 10,000 for these fiducial parameters. So that's the basic idea of what we're looking for. So now that's the signal that we have in mind. Let's talk about what kinds of stars provide candidates for finding this signal, given what we know about white dwarfs in our solar neighborhood. So the Gaia survey is mapping out, they're finding stars throughout the Milky Way and measuring their positions with high precision. White dwarf stars are especially dim, only 1/10,000th of a solar luminosity, so we're not going to get to see all of the white dwarfs throughout the entire galaxy, but we will be able to see, and Gaia thinks they'll be able to see all of the white dwarfs within about 100 parsecs of the Earth. I don't really need to see the ones past there because the signal I'm talking about, the flux will drop like whatever distance. So I don't gain from knowing that there's a very bright white dwarf on the other side of the galaxy. And their current catalog, which I should probably put in quotes because they may have released another catalog since then, I haven't checked, contains about 70,000 white dwarfs. So they've already identified lots and lots of white dwarfs in our stellar neighborhood. Now, Gaia just tells me where the stars are and it tells me about their luminosity. It doesn't tell me how strong their magnetic field is if they have one at all. We expect that all of those stars should have a magnetic field, but we have to actually make a measurement of that field strength. So how do we do that? And so the best way of measuring the magnetic field is using a Zeeman effect. The idea is that we're looking at the spectrum of hydrogen in the star, and the splitting of the spectral lines are split if the hydrogen atoms are in the presence of a strong magnetic field. So this, I apologize, this plot is almost invisible. I know it's very faint, but what it's showing is a sequence of spectra from different white dwarf stars, where the dashed lines are trying to guide your eye towards 3 spectral lines, and the stars at the bottom have a weaker magnetic field, 1.5 Gauss, 1.5 megagauss, 3 megagauss, 7 megagauss, and the star at the top has 42 megagauss, and you can see how the lines are being split more strongly for the stronger magnetic field. So this is how we actually infer the field strength of different stars. Now, for this one star, REJ031783, there's also information, time resolved spectroscopy. So as the star spins around, they're making these spectroscopic measurements and watching how the spectral lines are changing, which is telling us about the field strength for that star pointing towards the Earth as the star spins around. And so that's what I meant earlier in response to the question about whether we can learn something about the structure of the magnetic field. So from looking at that, you can actually see that the star's magnetic field is fit really well by just a dipolar profile. In fact, they claim it's fit a little bit better by a dipole that's slightly off center from the center of the star and slightly tilted from the axis of rotation of the star. But you can start asking these kinds of questions about what's the structure of the star's magnetic field. So anyway, we've got something on the order of a few hundred stars for which we know where they're at, how far away they are, how hot and bright they are, and their magnetic field strength. So we can take that list of stars, estimate an expected Axion-induced X-ray emission from each of them, and rank the list. And so here's the top 10 stars on that list. The top one is the star I've already mentioned a couple of times, REJ031783. Its mass is the highest of the top 10 at about 1.3 solar masses, and its radius is around 0.04 stellar radii. It's not the brightest of all of these. It has a luminosity of about 0.012. And a corresponding surface temperature of about 30,000 Kelvin. Its inferred magnetic field strength is around 200 megagauss, and Gaia measures its distance from Earth with high precision to be about 30 parsecs. And so the numbers on the right are just the corresponding X-ray emission for some arbitrary choice of Axion, Photon, and Axion electron couplings, just so we could do the ranking. So we can focus our attention on this top star now and look at it a bit more closely. So this star was actually identified as, it's been called the hottest known highly magnetic DA white dwarf. DA just means it's got hydrogen in it. And it was first observed by the ROSAT instrument in soft X-ray, so meaning energy is a bit below a keV. And they did follow-up observations in optical and far UV. And this is that spectroscopy I was referring to, in which as the star is spinning around, we're looking at how spectral lines change. The splitting tells us about the strength of the magnetic field, and this evolution tells us about the effective strength of the magnetic field pointing towards Earth.
So, may I interject?
Yeah.
Okay, so Earth is 6 times 10 to the 8 kilo electron volts. So we've got to multiply by that number up to get to the actual flux per centimeters per second. So I have to say that because I cannot do words in my head.
Yeah, thanks for the reminder. Yeah, I should add. Yeah, I also did not remember the conversions for that one off the top of my head.
So maybe one question. So I understand that you can measure the strength of the different,
I mean, you cannot. What I was referring to about how they do this modeling is asking whether the spectral information is better fit by a dipole that's at the center of the star with its axis, with the dipolar axis aligned to the rotation axis, or they can vary it. You can offset the dipole from the center of the star, or they could twist the dipole with respect to the center of the star. But all you're doing is changing the effective field strength that we're seeing. You're not actually making information, you're not measuring information about the orientation of the magnetic field.
By the way, these are small fluxes, but they're doable. I mean, like realistic.
That's right. Is that a question or a statement?
No, it's a statement.
Okay, thank you.
By multiplying the number on the screen by the number.
Right. Yeah. Okay, very good. So now this star is, I told you at the very beginning of the talk that we don't know if these types of stars are emitting hard X-rays because we haven't looked. This star is very special. It's this very hot and relatively nearby indirect dwarf. So for this star, we did look. And as far as I know, this is the only star that there's been an effort to observe it in hard X-ray. The Suzaku instrument spent 60 kiloseconds looking at it, which I think is 20, 30 hours. And they didn't observe any X-ray emission. They placed a limit on the X-ray flux from 2 to 10 keV at this level. And now, having not observed any X-rays, we can recast that as a limit on this scenario in which axions are emitted and converted into X-rays.
Were they motivated by precisely this? Or
I think my understanding is that it's just this star is kind of peculiar in the sense it's very hot. And as far as I know, they recognized that it was potentially special and wanted to look at it for that reason. They did not know anything about axions, at least, as motivation. But that it'll be a little bit different. So now Chandra is going to look at it again because we asked them to look for axions. So here we are back to the axion parameter space. Horizontal axis is axion mass, where we're looking sub-eV masses. Vertical axis is now the product of the axion photon coupling and the axion electron coupling. We use one to produce the axion at the core of the star and the other to convert it into a photon in the magnetosphere. The familiar KSVZ axion band is down here. And the that limit I said you could derive from Suzaku is shown in blue. So any point above the blue curve would have overproduced X-rays, and Suzaku should have seen it. The blue curve is a couple orders of magnitude below the previous best limit from CAST, which was looking for a similar effect from our own sun. And they also derived a limit on the product of the axion electron coupling and axion photon coupling. But you could do a lot better. So Suzaku doesn't have the best point source sensitivity, and they were making the measurement many years ago. With an instrument like Chandra, you could potentially get a much better limit, even for a smaller observation time. And so that fact is what motivated us to go ask Chandra if they would spend some time looking at our favorite star. Oh, before I get to that, let me just mention one more thing. So there's uncertainties when it comes to modeling the star. We weren't doing any modeling of the star for this study. We were relying on the astronomers to provide us, or particle astro people to provide us with the models. But whenever possible, we did the conservative thing. So for example, this study of REJ 03753 considered different nuclei in the core, whether it's a carbon-oxygen white dwarf or an oxygen neo-white dwarf, and different choices for its effective temperature and luminosity. And so to draw those limits I showed in the previous slide, we were taking the most conservative thing, the lower temperature, whereas if I had been more aggressive, we would have had an even more aggressive limit as well. So just to give you a sense of, we're aware there are uncertainties and we're trying to do the conservative thing.
So can you remind me again, why do you lose sensitivity to the QC vaccine?
Yeah, so sorry, yeah, great, good point. So this has to do with the axion photon mixing. So I'm producing axions way up to keV. Everywhere up to keV, I'm still making axions at the core of the star, but I get a suppression due to the axion photon mixing, which becomes inefficient for too large axion masses, because I'm effectively putting an on-diagonal term. I'm effectively putting an on-diagonal term into the mixing matrix. Right.
It's just, you need couplings, which are much larger than predicted for the QCD.
Yes, that's right. So I mean, for instance, to be consistent with the Suzuki, I mean, I don't know, here at 10 to the -3, they don't even sit on the curve together, basically, but I mean, to be consistent with Suzuki, I have to be there or above, whereas GCD Axiom would have me down here. Is that? Or another question is about why do we lose sensitivity as we start cranking up the Axion mass?
Yeah.
Yeah, it has to do with the Axion photon mixing. So essentially, there's
Why there is a structure in this one?
that's just because there's different terms. There's different terms in the mixing matrix, and when different ones get comparable to one another, you get these types of features in here.
Are you going to go back to the matrix just to point to us?
Yeah. So yeah. So for instance, I'm sending in these axions on shell. So omega squared is equal to k squared plus ma squared. We'll zero that one out. But these other two entries. This you should forget about. This is the photon mass that I didn't need to write down. So this becomes effectively ma squared over twice axion energy. And as I start cranking up the axion mass, I'm putting a bigger and bigger on diagonal entry to my matrix, which eventually just suppresses the axion photon coupling. So it suppresses the axion photon conversion. Right. Yeah, but you're making axions as long as their mass is below keV or so. It's just that they're no longer efficiently converting into photons.
Does the assumption that these things are related to dark matter play any role here?
Yeah, when we're making our own axions in the star,
Right.
so whether or not they are dark matter doesn't matter.
But the choice of coupling is none of that. 'Cause that's all.
Yeah, there's no relic abundance constraint imposed on top. I'm assuming that the parameters that end up here, either if you want them to be dark matter, we have to have another discussion about whether these parameters are consistent with that and what's the production mechanism.
I guess that's the other.
You can link to another anomaly as it's.
Well, sure, and then there
You can
would be
link it, yeah.
another decay constant.
You can link to another anomaly, because what I meant is the cooling hints.
Right.
That's the statement of one, that some.
Yeah, I didn't mention that, but maybe it's worth pointing out. In a variety of systems, white dwarfs, horizontal branch stars, red giant stars, these stars appear to be cooling anomalously quickly. And one way of interpreting that is the result of Axion emission or some other dark photon or whatever have you, new particle from the core of the star. And so then that favors a non-zero axion electron coupling because you need to get them out of white dwarf stars, and a weakly favors a non-zero axion photon coupling, and weakly means like 1 sigma favors a non-zero axion photon coupling. So the product of those two best fits is this dotted line. So you could also say that we've constrained the cooling hint scenario over here, but I didn't say that because the axion photon preferred non-zero value is only 1 sigma away from 0, so it's pretty weak. I think you might see that again on one of the plots a bit later too. But I mean, to be fair, the cooling hints certainly provide one reason why you might want to make the types of observations I'm talking about. Right? If you think that axions are responsible for this anomalous cooling, you'd like some other way of testing that idea. And presumably we would try to see the axions. So it's natural to ask whether I could use the observation of those axions as a way of testing the cooling hints. All right, can I, it looks like I'm at the end of the hour, but can I continue with people? Of course, okay, very good. So I think maybe another 10, 15 minutes, maybe 10 minutes. Okay, that was the bottom line about REJ 03853. And then as I mentioned at the beginning of the talk, we were very lucky to have Chandra doing a call for proposals just as we were putting out that other paper. So we submitted a proposal and we asked them, can you please look at our top 4 stars? And can you please look at them for quite a while? They don't have to look at it as long as, they don't have to have as long an observing time as Suzaku because their point source sensitivity is better. They get more data at less time. We asked them to look at the top 4 stars. Like, why would we look at the top 4 stars? Because your top star is the best star. We're just going to look at that one. We're like, that's a good point. So they only looked at REJ02785 but I think it was a pretty good case for them to spend time doing these observations because either they'll discover an X-ray emission which isn't supposed to be there, and then we have an exciting scenario where we're trying to explain where these X-rays are coming from, if it's from new physics, if from some unknown astrophysics, and so on. Or they don't discover any, they don't see any X-rays, and so we're in the same scenario we had with Suzaku, where we're setting limits, but the limits improve by over an order of magnitude. Before I tell you, oh yeah, and then, so here's my artist's impression of what the data taking looked like. It was a satellite, so it's not as if, but it was December. I suppose somewhere in December it was cold. Maybe this is what it looked like upstate Minnesota that time of year. They were supposed to do the observation many months. Has anybody recognized? Right. Don't know if anybody recognizes this, if it's actually. Yeah, they were supposed to do the observation many months before, but there was this pandemic, I don't know if you heard, which delayed things. Before I tell you what Suzaku saw, let me briefly mention some of the things we were doing in the meantime. So now, rather than thinking of a whole bunch of stars, we're focused on one star, so we can try to do the modeling of that star a bit better, whereas before we weren't modeling at all, we were just relying on the modeling done by previous studies. And this is largely the work of Chris Desert, a student who's now at Berkeley. So we're performing these white dwarf cooling simulations with this code MESA. In order, you start out with a hot, bigger star, let it exhaust energy in various channels, and it becomes a smaller, colder star. And you get different predictions for its age and color today and brightness today as a function of what mass it has. And so this axis is color, this axis is brightness. And the three different curves here correspond to three different potential masses that the star might have. And that data point in the center is what is actually measured for REJ03753, which seems to be consistent with a mass of about 1.22 solar masses. So we're going to use 1.22 solar masses. Before, the astronomers told us to use 1.3. So this is revised downward a little bit, but it's only a 10% change. And since the star is a bit smaller, its core temperature is also a bit lower. And so the best fit core temperature now is around 1.4 keV, whereas before, if you remember, it was around 1.7 keV. So again, that got revised down by about 10% or so, 20% or so. This just give you a sense of the level of accuracy we're going for, at least insofar as the types of factors that we're worried about. The other thing you can do from studying the cooling history is learn something about the composition of the star, the chemical composition of the star. And so for those best fit runs I showed in the previous slide, the composition was predominantly oxygen and neon. And this is a plot of essentially the radius distance from the center of the star, the enclosed mass, and then the relative fraction of different nuclear species. And so that's useful because if you remember when we did this Bremsstrahlung calculation, we need to know Z and A and some extra medium dependent factor. So now this allows us to, this informs our choices there. And so that's shown here. So here I'm showing an expression for the emissivity, which is the energy output per unit volume per unit time from some point in the star. You have to integrate emissivity across the entire interior of the star to get the total luminosity. And it's the same factors I showed before, except now I swapped omega, e's to omegas for some reason. It's the same thermal energy spectrum. It's all the same factors over here. And then there are these factors over here that were medium dependent. And we want to sum over the different species of ions that are present inside the star. One interesting thing is that there's this medium dependent factor F that I told you last time we just set to be some order 1 number. And it is some order 1 number. So what we were doing before was fine. But now we can do a slightly better job because if you vary as you move closer into the interior of the star, things are getting more dense. And whereas the ions are in a liquid phase towards the outside of the star, they enter a solid phase inside the core of the star. And that leads to some suppression due to correlation effects. This is why you see these jumps in F. So suffice it to say, by actually doing a dedicated analysis of looking at REJ03753, we're able to get a more precise handle on what exactly the Axion-induced X-ray signal should look like.
So did you do this solid state effects yourself, or is Ring calculated?
Yeah, again, there are some classic papers from the 80s that there's a numerical calculation of this factor F as a function of density for the solid phase and liquid phase. We rely on their results, but now we feed in our densities and chemical compositions. Yeah. So the expected signal would look something like this. The top left panel then shows the axion luminosity in these energies from 2 to 8 or 2 to 10 keV. The top right panel shows the axion photon conversion probability. And so the product of those two is the signal of the axion-induced X-ray flux. And then convolving that with the Chandra effective area gives some effective count rate. So what did Chandra actually see? So the left panel shows the field of view, where the black dot is RJ 0.7853 at the time of the observation. And each of those little boxes is an X-ray observation. It's an X-ray. And this is the expected signal template here. So if we move that onto there, we'd expect to be seeing a lot of colored boxes right around the star, and there are not any colored boxes around the star. So Chandra did not observe any X-ray emission from REJ 0.7853. And so again, we're in the same situation we had with Suzaku, in which, since no X-rays are observed, we'll be able to quote a flux limit. They give us a flux limit. We could translate that into a limit on the axion couplings to matter. One kind of interesting thing here was there was a bit of a panic because stars move around on the sky. And so when we told them where to look, we were using the last known location of this star. And then when they actually had done the observations, like, did we update that to where the star is now? And when we weren't seeing any X-rays right after opening the data, we were very worried for a short period of time, like one afternoon, that we had asked them to look at the wrong part of the sky. And they completely missed the star. But the difference between where the star was supposed to be and where it turned out to be is not very large.
But what are those dots in the middle?
Well, the dot in the center is where the star should have been when they were doing their observations in December 2010. And the red dots are where the star was previously when we were asking them to make the observations, just to give a sense of how much the star moved in a few years between when Gaia observed its position and when Chandra observed its position in
And the
X-ray.
scattered squares that are,
Each square corresponds to an X-ray that was observed, and the colors correspond to the energy of the associated photons.
and these are just random.
I mean, there's some amount of diffuse X-ray emission. I don't actually know if these counts are consistent with the expected diffuse X-ray emission, but they're not sufficiently close on the sky to where the source is to be able to associate with the source. Essentially, if you take this circle and scale it up to there, then there would be essentially 4 pixels around there, which is where you'd expect. If the source were emitting in X-rays, we would be seeing 4 colored pixels around here. We are not.
Presumably the size of those squares is the resolution.
Yeah. It's the size of the pixel, yeah. Yeah, I guess the other thing to comment on here, not to belabor the point too much, but it's a lot of work to ask a telescope to make a measurement. This is the one and only time I've ever done it. And to be honest, the student Chris Desert did 90% of the work. You have to read the manual and figure out what settings. And it's not like there's a lot of filters and which filter you want to use. So Chris did the lion's share of the work in getting us set up to do that properly. So
You have to tell telescope people what was said.
yes.
They don't do it themselves.
Yes, there's not like somebody's helping you and cross-checking, at least not with this experience. I mean, this is my only experience doing this.
Where
But
does it trend from?
where does what, sorry?
Where does it trend from?
It's a satellite telescope.
Yeah, I understand. Where's the mission
Oh, where's
control?
L2 or I don't, where you're asking? Oh, the command center. Oh, sorry. I don't know. Yeah, I don't know. Sorry, I thought you were, where does it run from? I don't know. Yeah. Yeah, maybe being in Houston with NASA nearby, I should know where these things are getting run, but it's probably, yeah. I don't think we could have driven down to Galveston and asked for their help either. So very good. We're almost done. So now the limit can be expressed in this way, rather than showing that before I was showing mass and product of the couplings, but you may have noticed that if we go to low mass, the limit became insensitive to the mass, or we're getting a horizontal line on the previous limit plot. So here we'll just focus on low mass, and we can look at the parameter space of the Axion electron coupling and Axion photon coupling. And so this is the limit from the non-observation of X-rays by Chandra. This is our previous limit from the non-observation of X-rays by Suzaku, so we've improved by about an order of magnitude. This is the limit from on just the Axion electron coupling from white dwarf cooling. If you were to the right, white dwarfs would be cooling down too fast. And then this one up here is the limit on Axion emission from our own sun, from the Axion photon coupling. And just coming back to the cooling hints, I mentioned how the cooling hints in a variety of different stellar systems favor a non-zero coupling of axions to matter. So the best fit point is this dot that's very now ruled out by our limit. And the 1 sigma containment region looks like that. So like this is what I was getting at earlier. There's a strong preference for non-zero axion electron coupling and an incredibly weak preference for non-zero axion photon coupling. So we're testing the cooling hints in the sense that that best fit point, according to one study by Gianotti a couple of years ago, is now excluded. Okay, one last thing here, which is just, wouldn't it be nice if I could show you a plot which is just axion mass and axion photon coupling, because everybody always shows the axion mass, axion photon coupling. And I've got this axion electron coupling in the way, which is kind of annoying. Can't I get rid of that? Well, you can get rid of it if you imagine that the axion electron coupling is being radiatively induced from the axion photon coupling through a loop graph such as the one shown here. And so it's a classic paper by Shrednicki where he does this calculation of axion photon and radiatively inducing axion electron. Here we're going to do something similar, except in the UV, it's really axions being coupled to SU2 isospin and U1 hypercharge that radiatively induce in the IR axion electron couplings. And so you calculate its beta functions. There's some very nice papers by Matthias Neubert and company who've done this in recent years. And this gives an expectation for the axion electron coupling given some axion gauge couplings in the UV. Now, there could be some cancellations. Essentially, this is the axion electron coupling in the UV, and maybe it's tuned against those. It's very small or something. But if we suppose that this axion electron coupling in the UV is 0, then, and these two guys are not somehow fine-tuned against one another, then we'd expect the axion electron coupling in the IR to be at the level of 10 to the minus 4 axion photon coupling in the IR. And so here we are then in the axion photon parameter space that it's customary to look at. Again, if you do something somewhat optimistic, you'd suppose the axion electron coupling is comparable to the axion photon coupling in these some special units. And then our limit would show up here as this red line. But if you do the pessimistic thing I was just talking about, where axion electron coupling is radiatively induced from the axion photon coupling and it's down by a bunch of 16 pi's and things, then our limit would be shown right here. So we do a little bit better than CAST in this mass window, but the limit is comparable to CAST. So that's kind of saying something. Even in this worst case scenario where somehow in the UV axion electron coupling were vanishing, we would still get a non-zero axion photon in the IR and an associated limit on it. And somebody asked about Electro-Primakov earlier. Electro-Primakov, you asked, where's if I couple the axion to the photon propagator, the limit for that would be up here somewhere. So it's not any more constraining than CAST.
What I care about is really the axion coupling.
Oh, sorry, yeah, you asked about nucleon. I brought up Primakov.
I do expect the photon one.
Yeah.
The nuclear one, I thought that would be generically bigger.
Yeah, it's just not as, it's not as good. There's similar constraints on the axion nucleon coupling from other cooling channels in other stars, ordinary stars. And there's a similar story about how the constraint you get here is weaker than some other constraints. All right. The only last thing to say is, if we had actually observed an Axion emission, this would probably be we'd be having a different conversation where I'd be trying to convince you it's coming from axions. There are some reasons that you could easily discriminate whether the emission's coming from axions or astrophysics. So now I'm not an expert in the astrophysics of how you'd get hard X-rays off of compact stars, but with somewhat of an appeal to authority, I'll just point out that the only discussion of getting X-rays at these energies from white dwarf stars is if they're either in a binary system with a companion from which they're accreting, or there's a disk from which they're accreting. And even in those two cases, the spectrum would look something like this, where it's falling at energies above a keV, whereas the signal we're looking for is rising at energies above a keV. So presumably with enough spectral information, you'd be able to tell them apart. And moreover, there's lots of other ways you could tell if it were actually axions by looking at different stars. You get some time dependence as you see the star spinning around and its magnetic field strength changing. You could potentially get polarized X-rays because the orientation of the magnetic field is linked to the polarization of the photon you produce from the axion. So lots of other handles that can be used to search for whether the X-ray emission is astrophysical or whether it's from axions. All right, and that's it. Just to reiterate, we've been trying to think of, there's a variety of probes of axion-like particles that are terrestrial, cosmological, and astrophysical in origin. And here we've been trying to make use of existing observations of compact stars in X-ray and propose new observations of compact stars also in X-ray to try to uncover evidence for these axion-like particles. The observations by the Chandra instrument didn't find any X-ray emission, but by doing so, we were able to place the strongest limits to date on this product of the axion electron coupling and axion photon coupling. All right, thank you very much for your attention.
Thanks, Andrew. 15, 20 years ago, there was much talking about same effect from the sun, but I do not know if it ended in any limits or the risk.
Yeah, I forget the name now, but I gave this talk. I think it was
Yanis Simonides in particular, and Konstantin Zibas. I
see.
know the Axiom. I mean, like they're doing Axions for decades. Right.
Yeah, I'm trying to remember the name. There's an observer who mentioned to me that they were doing this now with the sun.
Sure. There are more instruments. We even have our own person here doing the solar X-rays.
Right. So yeah, there's lots of other opportunities. I mean, and then the other thing you might complain about what I'm presenting is it's predicated a lot on this one star, this one peculiar white dwarf, so it happens to be very hot. And it would be interesting to do similar analyses with other stars. I mean, I think Chandra had, I can understand that their time is valuable and they don't want to spend time looking at 4 different stars.
One can probably just do this simple, okay, I do not know about the effects of the plasma and the turbulence, but you lose in the strength of the magnetic field a lot, right? If you use the sun. But it's a
closer.
Right?
Yeah.
So I
That's
don't
right.
know what
Yeah.
the final tower would be, right? So
It's a lot closer, actually, yeah. Doesn't the closeness way overcompensate?
well, that's what I'm asking, right? Whether this is.
Well, the distance is 1 over the distance squared, right?
Yeah.
And the distance, from
Yeah.
light years to
Yes.
light minutes.
Yeah, the question, but there are other things that I do not know, right? The magnetic field is turbulent. There is plasma in the chromosphere, although
maybe the
it's
turbulence helps.
in the corona, right?
Yeah, you don't know that the turbulence doesn't actually help, doesn't amplify.
Yeah, that I don't know.
Right, because you need a constructive interference between different parts of your path. So
Yeah, I think.
why not do it for this?
Yeah, we should do it for
like,
this. I think.
I don't know, the Europeans just put a new gigantic satellite to a quarter distance to the sun.
Right.
Staring at it.
I mean, I know, for instance, Ken Van Tilburg has been thinking of looking at X-rays from the sun. He's doing this work on stellar basins where the axions are emitted and they're basically non-relativistic because they're out in the tail. Yeah, and then they decay. And so we did have some conversation about whether you could use, because he's got observations of the sun in the stellar limb off the edges. So potentially you could use the same data sets to look for this phenomenon as well. Yeah, that's a good one.
A factor of 10 to 10
From the distance.
And if
Yeah.
you're using, so it's a factor of 10 to the 5 because of the magnetic field. Is that the number?
Square, yeah.
Oh,
Yeah, we're going from,
oh, so but then it's about the same.
yeah, because you're going down from hundreds of megagauss to 1 Gauss. And
Yeah, hundreds of megagauss, so 10 to the 5, so it's squared is 10 to the 10.
Yeah.
Which completely compensates for the distance.
Yeah.
But
And I
then
think
you can
the-
observe for a lot longer.
Yeah, there's, I think the other issue is whether the sun is already emitting in X-rays. That's something I don't
Yeah,
really know.
you do it during the quiet sun.
But I mean, I guess the other related idea would be doing it with neutron stars, right? So as I said, Raymond Coe has done some work on looking at a particular set of 7 isolated neutron stars for which there exists X-ray data. In that system, they find evidence for an anomalous X-ray emission, and they interpret it as resulting from Axion to photon conversion. So you could ask Raymond about that. Sorry,
Speaker. He's in the speaker.
Raymond?
Yeah, I'm here. Yeah. Do you hear me?
This system is not connected.
Do you hear me? Hello? Hello, do you hear me?
Yes, we hear you. Yes, go ahead.
Okay. Yeah, I couldn't hear what people were asking, but I do have a question for you. So is it possible that we also induce the axion nucleon coupling from the axion photon coupling? And in that case, where would the limit be if you include that production from the axion nucleon coupling?
Yeah, you would radiatively induce an axion nucleon coupling in the same way you radiatively induce an axion electron coupling. Parametrically should be the
I was
same.
trying to ask a question slightly differently.
Okay.
I will be happy to, turn off Axion electron coupling.
Uh-huh.
I wouldn't be happy to turn off Axion nuclear coupling. That's at least to be the same order as others. If I want to think it as reasonable connections
You're thinking about a QCD axion?
to strong CD puzzle, right?
Yeah, here we've kind of removed ourselves from. Can you hear? By the way, did you hear that, Raymond?
Yeah, I heard it.
You can't turn off the nucleon coupling. If it's coupled to the photon, you can't turn off the.
Yeah, I mean that's yes. I mean I'm not relying on the axion nucleon coupling for the analysis, right? Really, I should be calculating. I should be summing all the channels, right? And they did depend on different couplings. So some of the channel. I mean, I should be summing emission from here, here, and here, and they depend on 3 different couplings. So as I vary the 3 different couplings, I get one or the other dominating. All I was trying to say earlier in response to Jen's question is that there's already upper limits on all 3 of those couplings from different observations.
Most of the nuclei is probably already spinless. It's either oxygen or neon, right? So you don't need much from that
Because why? Sorry.
because the spin is zero.
You're saying the axion's coupling to the spin of the nucleon?
Well, I cannot couple to the mass, so then we will give the 5th force, so it will be all excluded.
Oh, I see.
Of course, it couples to the spin.
Yeah. Basically, we are asking whether how strong the assumption that you don't have nuclear coupling.
Yeah, I'm
That's
saying
a
what I'm,
very weak assumption. That doesn't affect your.
yes, it's a weak assumption. What I'm trying to say is even if I allowed an axion nucleon coupling and then cranked it all the way up to what the existing limits are on the axion nucleon coupling, and then I summed the contribution from axion emission in these 2 different channels, that the additional one would be negligible compared to the one from ramming it off the electron. Is that what your question was, Raymond?
Yeah, but why would you expect it to be negligible? I thought I would expect it to be of the same order.
No, I mean the masses are. I mean, like here, for instance, here the formula. This we have an electron mass down here. Beyond mass.
I see.
And technically, the limits are a little different too.
I see.
Yeah.
Okay, we have other questions?
All right. Thanks everybody for the nice questions.
Thanks a lot.
Thank you. Nice seeing you. Are you feeling okay, Raymond?
Yeah, I'm fine. Yeah, my family is healthy, so
Good. That's good. All right, I'll catch you later.
okay. All right, thanks. Bye.